and we'll get started. All right, talk about some air pressure here. We're going to find the inverse of exponential functions. By the way, finding inverses of exponential functions means that you are finding logarithms, because exponential functions and logarithmic functions are inverses of each other. All right, right here, air pressure. The air pressure outside of an aircraft can be determined by the equation P equals B times 10 times, is that an exponent? I can't even tell if that's an exponent or not. Is that an exponent? Let's see. It looks to me like, yes, that is an exponent. Okay, just the way it's written, I don't know if you were confused by that at all, but this rational value here, I can't quite tell if that's an exponent or if it's just being multiplied. It's an exponent in looking at this rest of the work down below. So that is an exponent. So P equals B times 10 to the negative 9H over 100th power, where B is the air pressure at sea level. B, I think, stands for barometric pressure. I don't know if anybody here has taken a science class and talking about weather at all and barometric pressure, but I'm fairly certain B stands for barometric pressure at sea level, and H is the altitude in miles. So H is the altitude in miles. It just tells you how high off the ground you are in relation to miles. So if you have a height of 5,280 feet, H would be 1, because there's 5,280 feet in 1 mile, and H is in miles. So we'll have to keep that in mind as well. If the air pressure at sea level is 14.7 pounds per square inch, which, anybody ever heard of PSI? That, yeah, like tires, inflation, things like that. That's what this is here. 14.7 pounds per square inch. Most of the time, tire pressures are a lot more than that. So you're basically exceeding the pressure of what's normally outside of the air in the tire. So, but we're talking about altitude here. Write an equation to find the height of an aircraft when the air pressure is known. So, anybody know what happens to air pressure as you go higher? What's that? Yeah, it gets lower. Yeah. The air pressure gets lower as you increase your altitude. So let's have ourselves a look. So B is the air pressure at sea level. So what it's saying here is, here's our original equation. Let B equal 14.7. So let's write 14.7 right here. So we got 14.7. By the way, are we solving for anything here? Are we figuring out the value of a variable on this problem? No. We are writing an equation to find the height of an aircraft when the air pressure is known, which we don't know right now. But we're solving for H essentially. So if you want to know what the height of the aircraft is, that means you need to get H by itself. So that's what we're doing. So this part of the expression over here is being multiplied by 14.7. So we'll divide each side by 14.7. That's what it shows right here. Then we are going to use our definition of a logarithm. So it actually gives us a hint off to the side. Recall that an exponential function is of the form x is equal to b to the power of y, and a logarithmic function is in the form of y is equal to log base b of x, where x is the original argument. So in the equation, h over 14.7 equals 10 times negative 9p to the 100th power, x, the argument, not the argument, but rather, yeah, this is the argument here, is equal to h over 14.7. So b is equal to 10, and y is equal to the exponent of negative 9p over 100. So here we go. We're going to write log base what? Right here. What's our base value of this exponential function? What number has the exponent? -9. So -9 is in the exponent, but 10 is the value that has the exponent. So yeah, 10 is our base. So we're going to say log base 10. And our argument here is what's on the opposite side from the power, which is P over 14.7. So that step right there should say log base 10 of P over 14.7 is equal to the exponent, which is negative 9h over 100. Now, what we're trying to do here is we're trying to get h by itself. And so if you remember, we've done this a few times in this class already. All we're trying to do is get h by itself. H is currently part of a fraction. So if you want to get rid of a fraction with the variable, you multiply by the reciprocal of that fraction, which is why right here, it says multiply each side by 100 over negative 9, or negative 109, however you want to do that. But I would actually put the negative here. Multiply by negative 109. Now we have to do that on both sides. And the negative 9s and the 100s will cancel, leaving us with h. And then you can see that that negative 100 over 9 has been multiplied here over on the left. The only difference is they've got the negative on the denominator. It doesn't actually make any difference whatsoever. If the negative is on the numerator or the denominator, or if it's just off to the side, it means the same thing. So here's a real life situation where you can actually use logarithms. Now, if we knew what the air pressure at the altitude was, if we knew the air pressure outside of the aircraft, we would actually know how high it's flying. But we don't have that information, and that's not what we were asked to do. Any questions about this conversion here? It's actually the exact same thing we were doing before. It just has slightly more challenging numbers and variables to deal with, but it's the exact same process. Questions before we continue? Oh, let's keep going then. So, what do we have? Yeah, we got a few more pages. Maybe we'll spend another day on this lesson. I don't know. So, tornadoes. The distance in miles that a tornado travels is y equals to 10 to the w minus 65 over 93rd power. All right. Where w represents the speed of the wind in miles per hour. Part A, write an equation to find the wind speed when the distance traveled is known. So essentially, write a logarithmic function and solve for w. Now we definitely are going to need to use some space over on the right-hand side here. So I'm just going to start over here and rewrite the function y equals 10 to the w minus 65 over 93rd power. You can see that. All right. So here we go. We're solving for w. We don't have any values for w or for y. So we're just doing rewriting this function as a logarithm in order to get w by itself. So if I was to start by writing log, what base are we using? 10. What is the argument? The argument is not the base. The argument is not the exponent. So what's the argument? Y. Good. Log base 10 of y is equal to the original exponent, which is w minus 65 over 93. So we got to get w by itself. Right now, w is kind of trapped up on that numerator, which means we should probably start by getting rid of the denominator. So what would be a good idea to do next if we want to get rid of that denominator? What's that? Yeah, multiply both sides by 95. So go ahead and do that. Multiply, or 93 rather. Yeah, 93. Multiply by 93. So that's going to give us 93 log base 10 of y equals w minus 65. By the way, notation-wise, when you multiply a logarithm, it's best to do the multiplication over to the left because it can get a little bit confusing because we're not multiplying this y by 93 because log base 10 of y, I need to make sure that everybody understands this. Log base 10 of y is a number. This whole thing, log base 10 of y, is some number. We don't know what number it is, but that number, log base 10 of y, is being multiplied by 93. So if you were to write log base 10 of y times 93, that would not work. Unless you put the whole log base 10 of y in parentheses and then put times 93 afterwards, just to show that you know that log base 10 of y is some number. It's some decimal value probably. So to kind of compensate for that, make it a little bit easier on ourselves, we'll say we're multiplying 93 by whatever the number log base 10 of y happens to be. All right, last thing. How do we get w by itself? Add 65, yeah. So we're just doing normal algebra at this point. So plus 65. And so we're going to end up with 65 plus 93 log base 10 of y is equal to w. So we'll just go ahead and translate that back over here. So w is equal to 65 plus 93 log base 10 of y. Great. Part B. Use the equation to estimate the speed of the wind to the nearest mile per hour of a tornado that travels 50 miles. All right. The distance the tornado travels, by the way, is y. So that means, in this case, y equals 50. So I'm just going to write it out here. Let's say W is equal to 65 plus 93 log base 10 of 50. That's the math problem we're dealing with. That's interesting because on Friday, we actually figured out what log base 10 of 50 was. Right here. Remember when I was asking if we know that 10 to the first power is 10 and 10 squared is 100, 10 to what power is equal to 50? And it was like 1 point something. So let's find out. So what you need to do here, there's two ways to actually do this, by the way, on your calculator. So the first way that we're going to do this is we are going to go to our math menu. So click on math. And then you can either, it's actually probably quicker to push the up button because that'll put you all the way down to the bottom of this list on math. And you're going to go to log base. And then for the base, we've got 10. And then we're figuring out the log base of 50. And that's the number that we got on Friday. It's about 1.7-ish. Don't use 1.7 though. Just keep going with this and just write times 93. Times 93. Plus 65. That's almost exactly 223 miles an hour. Cool. Now we could have just typed this all in at the same time. We could have said 65 plus 93 and then log base 10 of 50. And it ends up being the same thing either way. So you can actually just type it in exactly as it appears on your paper. Now, the other way to do this, because we're dealing with log base 10, and this only works if you have log base 10. There's a button on your calculator next to 7 and it says log. You can use the log button right here as opposed to the math menu, so long as your base value is 10. Log on your calculator means log base 10. So we could say 65 plus 93 log and then 50. Because you don't have to type in the base value because it's just assuming that you know that you're dealing with log base 10, which we are. So that should give us the exact same answer again. There's a few ways that you can interact with your calculator to get to the same answer, but either way, to the nearest mile per hour, well, that's obviously 223. So that's our answer. $223 miles per hour. Cool. Got it. All right. So questions there before we continue? All right. So the next thing I'm going to do before we start taking notes, I'm actually going to get into the online platform here, which means I need to change share that instead. Okay. So I'm going to head into the online side of this, because there's an interactive warm-up that we can use for this next portion, and I feel like that will be pretty beneficial. So that way you can actually, with graphs in particular, it's always nice to see things moving around as opposed to just being told what's happening, being able to see that stuff in real time. I feel like it's always a bonus, so bear with me. Okay, transforming logarithmic function. There. Buried and down on the long list. So let's see. Cool. Okay, there it is. So we are dealing with some graphs here. I'm going to go ahead and read the stuff that's up there. Hopefully, I mean, I think you can kind of see this graph here well enough. Let me see if I can zoom it in just a little bit more. That's better. All right. So we saw a little bit of this briefly on page 399 on Friday, where a logarithmic function was the inverse. Basically, the x's and the y's were swapped. And so logarithmic goes up like this. Exponential goes up like this. Logarithmic kind of went like that. And so they were like, it was kind of like butterfly wings, like sideways. So right here, a function of the form y equals log base b of x is a logarithmic function. The graph of log base b of x is the parent function with function base b. Sort of like if you have y equals 2 to the power of x, you would also have y equals log base 2 of x if the base value was 2. The general form is here, y equals a log of x minus h plus k. We have seen these variables, a, h, and k, over and over and over and over throughout the school year. A, what does a do in a function? An a value in a graph, what does it generally do? Yeah, it controls the stretch or the shrink, right? You can make it steeper or less steep. That would be a stretch or a shrink. What happens if a is negative? Was that? Yeah, it reflects across the x-axis. Basically, like flips it upside down. The value of h, what does that one do? Yeah, left or right. Go this way or this way. K. Yeah, translates it up or down. So, by the way, if there's a number in front of x inside the group here, that would be a stretch or a shrink, but it would be a horizontal stretch or shrink. And if there's a negative in front of x, that's going to be a reflection across the y-axis as opposed to the x-axis. So these are all things that we've seen multiple times over the course of the year. So it's in some ways, it's kind of nice that we keep using those same 3 variables over and over. You don't have to learn new ways of transforming functions, which is nice. So, all right. So yeah, it says a, h, and k are parameters that transform the parent function. We specified what those parameters are. You can use this sketch to investigate how changing the parameters of a, h, and k and y equals a log base 10 of x minus a plus k affects the graphs in the family of logarithmic functions with base 10, and then complete some exercises. So what I'm going to do is just show you in real time, messing around with some functions. What do we get if we mess around with k, h, and a? And we already said that k is going to move the graph up or down, so let's verify that. Left, yep, down, up, okay, so up and down for k. H should go left and right, yeah, there it is, left and right for h. Okay, and then for a, if a gets more positive, the graph should get steeper. If a gets close to 0, it should get less steep until it gets to 0, and once it goes underneath 0, what's going to happen? going to flip upside down. It's going to reflect across the x-axis. So let's see it. And there it is, upside down. All the things that we thought would happen, all the things we said would happen are happening. Great. Reset. Cool. So with these quick exercises, drag point K, see what happens. All right. Describe any similarities and differences among the graphs as the value of K changes. Well, that's going to translate it up or down the amount of units. So here we go. Complete the statement. If K is greater than 0, what's our answer? Up. All right. Down here, drag the point H. If H is greater than 0, let's see. If H is greater than 0, what direction is it going? The H is the left or right. It's going left or right when H is greater than 0. Go to the right, yeah. So if H is greater than 0, the graph is shifted to the right. All right, let's see. I'm guessing this is going to be an A is less than 0 situation down here, but I could be wrong. Oh no. If the absolute value of A is greater than 1, the graph is, what's the word? Before I even show you the options. Stretched. Yeah, there it is. Hey, look at that. Cool. It's nice to know things before we do them. All right. So all this is doing is verifying what we already knew, but it's honestly, it's nice to be able to see it actually happen as you're moving around values and all that good stuff. So let's keep going. That was nice and quick. All right. Talk about some functions here. So the function log base b of x, where b is greater than 0, b is not equal to 1. This is a logarithmic function. By the way, in order to be a logarithmic function, your base value, not only can it not equal 1, it also needs to be greater than 0. And I think we actually saw this before with our exponential in our previous unit. When b was negative, do you remember what happened to the y values? Anybody remember? We only had 1 or 2 examples like it. But when b was negative, the points went like this. You remember that? 1 or 2 examples we had in our assignment where it was like, it was jumping back and forth between over the x-axis. That's not exponential, which means if it's negative, it's not exponential, which means if it's negative, the inverse of it won't be logarithmic either. So it's got to be greater than 0. B can't equal 1. That's what makes a logarithmic function. The graph represents the parent graph of the logarithmic function we just talked about. So here's our parent function. Type of graph, continuous, 1-to-1. Continuous just means there's a nice curve to it. You can connect all the points and it makes a function on your graph. 1-to-1 means for every x value, there's exactly one y value. And then our domain. Our domain should be the inverse of the domain of an exponential function because it is the inverse function of an exponential function. So whereas the range of an exponential function is y is all positive values, right? Our asymptote was 0 on a basic exponential function. It goes up like this. I'll go back here to show you real quick. Right here. The range is all values of y that are greater than 0, which means that the domain of a logarithmic would be x values greater than or equal to, or greater than 0, not greater than or equal to. Because instead of having a horizontal asymptote, the inverse of that would then mean we have a vertical asymptote. Is this making sense? Everything's kind of flipped from what it was. So, which means that, let's see, the domain here are all values of x greater than 0. The range, all real numbers. Which makes sense because the domain of an exponential function is all real numbers. So the inverse of that means that the range of a logarithmic would be all real numbers. Good? Everything's reversed or inverted rather. Our asymptote, instead of the x-axis, it's the y-axis, which changes from a horizontal asymptote to a vertical asymptote. The x-intercept, notice here, we're talking about an x-intercept because, how come? Why are we not talking about a y-intercept here? Because it's inverted. And is there a y-intercept? No, there is no y-intercept because it gets infinitely close. Here's the y-axis. It gets infinitely close to the y-axis, but it never actually crosses it. Therefore, there is no y-intercept. There is an x-intercept, and it's at 1, 0. Whereas on an exponential function, the y-intercept was at the point 0, 1. Everything's inverted. Symmetry, no. Extrema, no. Extreme basically means there's a highest or a lowest point, which doesn't exist. So here we go. For a function f of x that is undefined at a vertical asymptote, x equals c. So that value of c can shift depending on the value of h, right? If we move it left or right, that vertical asymptote is going to change where it's at, which means it's not impossible for a logarithmic function to have a y-intercept. It could have a y-intercept. It just means that you'd have to shift it left. So you'd have an h value that would shift it left, and then you could get a y-intercept. So let's see. The end behavior is described as x approaches c from the right, or as x approaches c from the left. So for the parent function, where b is greater than 1, the end behavior is as x approaches 0, that little exponent of a plus is right here. It's coming from the right side. So from the right, so from the right side, from the positive side, as x approaches 0, what happens to the y values? They go down real quick. They go down to negative infinity. And it shows you that right here. So if you're coming in from the right, so if you got coming in from the right on the x-axis, as x approaches 0 on the x-axis, y goes to negative infinity. Then it says, as x approaches positive infinity, y approaches positive infinity. Because if you're going this way, if you're going from the smaller ones and you go up this way, by the way, there is no horizontal asymptote. I want to make that perfectly clear. It looks like there might be, but this continues to grow upwards indefinitely. It just happens a lot more slowly. So there is no horizontal asymptote up here. There is no boundary that it's going to run into. It's just going to keep growing up and up and up. But it'll happen a lot more slowly than an exponential because it's an inverse. So as x goes to positive infinity, y goes to positive infinity. Okay. Got some more information here. Transformations. Good thing we already know a lot about this. So the big thing you need to remember, as always, is with your value of h. Because if k is positive, it goes up. If k is negative, it goes down. If a is a positive number between 0 and 1, it shrinks it or compresses it. If a is greater than 1, or if the absolute value is greater than 1, it stretches it. If a is negative, it flips it across the x-axis, it reflects it across the x-axis. With h, however, the horizontal translation, because there is a minus in here, if you plug in a positive value for h, this will still stay as a subtraction problem. So if h is positive, it still moves it in a positive direction, but it will look like a minus because it's being subtracted because the number you plugged in for h is positive. I hope this is making sense. We've seen it before. If h is greater than 0, it translates to the right. Because if you plug in a positive number for h, this will still be subtraction. That's what we're saying. So it will go to the right. If h is negative, this will be a plus, which means it's going to the left, which means h is negative because negative direction on the x-axis is to the left. And then the other translations we've already spoken about. So let's keep going. All right, graph each function. Find the intercepts, domain, range, and end behavior. So step 1, identify the base. F of x equals log base 6 of x. What's the base? 6. All right. And it says to use some points. So we got 1 over b. All right. So this is a little bit interesting. So honestly, I would probably just go with I mean, b is 6, so 1, 6 would be -1. So it says use the points 1 over b, -1, 1, 0, b1, 1 over b, -1, and so forth. So yeah, so b1 would be 6, 1. Now, if you wanted to, and my recommendation would probably be just to go ahead and put this in the y equals menu on your graph and go to the table of values and graph it that way. Draw a smooth curve. What is our x-intercept, though? Where does this graph cross the x-axis? Where's that red point? 1, 0. Yeah. So the x-intercept, 1, 0. There is no y-intercept. All right. The domain. All blank real numbers. Positive, yeah. All right. POS with the period after it, abbreviated. The range is all real numbers because it goes up forever, goes down forever, all the y values, okay? An end behavior. Now, if this one was horizontally reflected, this would not be 0 with a plus, it would be 0 with a minus because it'd be coming in from the left. But because it's coming in from the right, we're saying as it approaches 0, from a positive direction, from the right, so that plus means from the right. If you want to put a little note there for yourself as well, just as a reminder, from the right, as it approaches 0, from the right, coming in, goes down, x goes to negative infinity. So the answers are here for us, but understanding what this jargon means is a good thing. So as x approaches 0 from the right, the y value, f of x, goes to negative infinity, goes down forever. As x goes positive on the x-axis forever, y also goes positive forever. Happens pretty slowly, but it still happens. Questions about this? Good so far? Ish? Okay. In terms of graphing these, let's just go ahead and do this next one. We can graph this next one. What does b equal on the next one, by the way? 1/4. All right. So 1/4 is the value of b. Now, if you want to just go ahead and graph this, go to your y equals menu, clear out anything that's in there so far. If you have your plots turned on, if any of these plots are highlighted in black, unclick them. And get rid of any functions that are in your y equals menu at the moment. Let's see, we got 10 more minutes today. We'll probably finish up tomorrow. It's fine. I'm not in a rush. So, log base. 1/4. You can use a decimal if you want to. I'm going to use a decimal just because I don't want to go back to the math menu and enter a fraction. So 0.25 of x. And then we can look at the graph, and it should look exactly the same as this one right here. So hit graph, and sure enough, I mean, it doesn't look precisely the same because the x and y axis are a little bit like the scales are a little different. So not a big deal though, because it is the same function. All right, so use points. 1/b for x and then -1 for y. We got the point 1, 0 and the point b1. So 1 divided by 1/4 is what? Was it? 1 divided by 1/4 should be 4. Okay. Which gives you the point 4, -1. If you look on the graph, when y is -4, sorry, when y is -1, x is 4. So yeah, 4, -1. We have the point 1, 0, and we have the point 1/4, 1. So those 3 dots on our graph are the 3 points that are being used here. Now, again, if I was doing this one by myself, I wouldn't necessarily do it this way. I would have my function here. I would go to second, graph, and then go to the table of values, and then approximate those decimals on my graph, because that would also allow me to get a lot more than just 3 points. In fact, any graph you ever make, if it's not linear, which this is certainly not linear, if it isn't linear, you should have a minimum of 5 values. That way you can get a good feel for how that curve is actually going to look. So graph the ordered pairs, draw a smooth curve. All right, x-intercept. What is it? Where does it cross the x-axis? 1, 0 again. All right, so 1, 0. There is no y-intercept. Domain. Yeah, all positive real numbers again. Because we're looking at x values here, right? Even though our value even though it's, you know, doing this thing here, right? It's going down as opposed to going up. It's still going to be positive real numbers for X because everything XY is positive. Range is all real numbers, and then we've got the end behaviors. X approaches from the right as it goes towards 0. What happens to the Y values this time is that as X approaches from the right? They go to negative infinity this time? No, they go to positive infinity. So they just go to infinity. Now, as X goes to positive infinity, the Y values go down forever. So we can see that. All right, more transformations. Let's keep going. We do have about 6 more minutes. I'll give you some work time tomorrow as well. So we'll probably finish up the last 1 or 2 problems tomorrow. We'll finish this page here, and then we'll finish the last 2 examples tomorrow, and then you'll have the remainder of class to just practice some logarithms. So transformations here. 2 log base 10 of x plus 3 minus 1. So here we go. Lots of transformations happening. Something that I do sometimes is just write out that basic form. Like that. Makes it a little bit easier to see what the variables are, because you can just do a one-to-one comparison. So because the number in front of the logarithm that is multiplying it has an absolute value of greater than 1, that means the graph is what vertically? Value of A is 2, which has an absolute value greater than 1. What's happening to the graph vertically? Stretch, yeah. It's being so stretched vertically. Stretched vertically. All right, because H is less than 0. How do we know that H is less than 0? Because there's a plus, yeah, which is a little bit weird, but go back. And here, the function itself has subtraction. And I wrote it again right here as well. The function itself has subtraction, which means that if this is a plus, that means the number that was substituted in for H has to be negative. And if something is being shifted negatively on the x-axis, it is going what direction? Left, yeah. So H is -3. It's going, it already says left. 3 units left. It wanted the number, not the direction. It told us the direction. All right, so it was shifted left, which actually means we end up with a y-intercept this time. K is -1. It's been translated 1 unit, what direction? Down, yeah. All right. So identify the ordered pairs of the parent function. Again, this is not a step that I would necessarily expect you to do. I would just say, go ahead and plug that into your calculator, see what it looks like. This is just obtaining points on the graph. That's fine. Plot the points, draw a smooth curve. So we can kind of ignore these steps here. You can just type it into your calculator. Let's go ahead and finish up this translation though. Oh, wait. No, that was it. It's just a graphic. Never mind. We're good. Okay. So we'll stop there for today. Didn't even want us to graph it. That's weird. Or I mean, talk about the transformations.